All right, so starting this problem, when we're factoring it, the very first thing you do is you look to see what you can divide out of every single term. What can you divide out of every single term in this one? Yep, there's a 5 that we can pull out. Is 5 the only thing we can pull out of every term? No, we can also pull out some x's. How many x's can I pull out of every term? 4, exactly. So I'm going to pull out 5x to the 4th at the start. And so that's going to leave me with x squared plus 4x plus 12. Now you'll notice at this point that it's an x squared. So we have a chance at least of being able to go on to the 2 sets of parentheses. So if you haven't yet, see if you can go ahead and factor it down to the 2 sets of parentheses as well. Now we know that we can go that far if we can find two numbers that add to the middle number and multiply to the last number. So, is there such a combination of numbers that adds to 4 and multiplies to 12? No. It's not looking promising. Some people have come up with 6 and 2, which is pretty close. But in order to add to the positive 4 there, it'd have to be a positive 6 and a negative 2. And the positive 6 and the negative 2 would give me a negative 12 when I multiplied them. And so that's why that doesn't work, is because the signs just don't quite line up. It's pretty close to working, but that does not work. We cannot find a pair that actually adds to the 4 and multiplies to the 12. So just pulling the 5x to the 4th out is all we can do. That is your final answer. That is our factored form. So then, this is one of those big themes that we've been taking a look at recently, is this whole idea of factoring. Another big idea that's woven throughout the entire year is our logarithms work. And today we're even going to do a little bit more with our logarithms, but we want to start with what we already know with logarithms, which is just rewriting the exponentials as logs and the logs as exponentials. So please do that for these 4. And hopefully you got this down where you can do it just straight from memory. But maybe you need to look back at your notes and find it. Or perhaps even you can't find it in your notes, in which case you'd be kind of feeling especially stuck at the moment. Well, if that's where you're at, this is what we're using. This is what you should find in your notes if you don't remember how to do it off the top of your head. And so for that first one, we're writing the exponential that we're given into log form. And the very first thing we write is log then, when we write it as a logarithm. So it's going to be log base something. Now the base is always the base of our exponential. So whatever's been raised to the power there. So it's going to have to be base 2. And then it's going to be of something, and that's going to equal the exponent. Well, notice the 1,000 is the part that's left, so it has to be log base 2 of 1,000 that equals x. And so that's our logarithm form. The next one's the same idea, except it's using all letters instead of having some numbers in there. We still start by writing log. Then the base is the base of the exponential. So that's going to be log base r. It still equals the exponent. And so it's going to be log base r of a equals t. All right, and then going the other direction on the right-hand side here, we're writing each of these as an exponential. So the very first thing I write when I write the exponential form is the base. The base here is the base of my logarithm. So it's going to be 3. And then it's going to be 3 to the power of, well, log always equals the exponent. So my exponent must be the 4. So it's 3 to the power of 4, which, yes, does actually equal 81. So the numbers even check out and tell us that we're doing this right here. All right, and then for the last one, log base t, so t is my base. It equals r, so r is my exponent, and therefore it must equal p. So t to the r equals p for that last one. And all we're doing on these is just the same old switching between exponential and logarithmic forms that we've been doing all year long. And why have we been doing it? Because I promised that we might go someplace else with it. And so today we'll start going someplace else with it, and then tomorrow we'll even break out the calculators a little bit. But today's going to be all figuring out the value of logarithms without having to resort to a calculator. So we're going to start with this one. Go ahead and write down this problem. And then we'll talk about how we actually can know this value without having to break out a calculator at all. Now, based on what we currently see, it doesn't necessarily seem straightforward to do, and yet it actually will be as we start seeing how to kind of find our way through these. And a great way to start it is starting with the one thing we do know how to do with a logarithm, which is to write it in exponential form. So if I write this in exponential form, it's going to be 9 to the power of x equals 81. Well, 9 to the power of what does equal 81? It would be 2, because 9 squared is 81. Now, it can be awfully tempting to be thinking 9 is your answer, because you're thinking, oh yeah, I just have to multiply the 9 by another 9 to get 81. But of course, x is the exponent. It's saying I have to multiply 2 9s together to get the 81, so that's why it's the 2. Now notice basically then what this tells us about how we can find these values. In this case, I actually had the x written in there. Well, you didn't even need the x there, really. Because as we look at something like this, where we see log base 9 of 81, notice that basically meant 9 to the power of what equaled 81. Whether we have it set equal to x or not, we could figure it out the same way, as you will see here. So with that idea in mind, please find the value of x in both of these equations now. So for that first one, the first thing I'm going to do is I'm going to think of it as an exponential. So that would mean 5 to the power of x equals 25. Well, 5 to the power of what would equal 25? Equals 2. All right, so we got 5 to the power of x equals 25, therefore 5 squared equals 25, so we get the 2 there. This next one, we end up doing 8 to the power of what equals 8. What would my exponent have to be here? 1, yeah. Because anything to the power of 1 is itself. And so that's why x here would be equal to 1. Now again, notice though, I didn't even need the equals x to figure out what the logarithm equaled, because really in each of these cases, I just figured out what the logarithm equaled. The x just gave me something a little bit more concrete to kind of hang my hat on as I went through it. But using those same techniques, we can figure out both of these values now as well. So go ahead and evaluate each of these two logarithms, again, without needing a calculator. All right, so for that first one, we can still look at that logarithm and read it as 2 to the power of what would equal 8, because that's really what a logarithm means. And so, even though I didn't call it x, I can still figure out what that exponent would have to be. So 2 to the power of what would equal 8? 3. And so our answer here is just 3. All right, and then for this last one, it's going to be the same idea, where I'm saying 4 to the power of what would equal 1. This one for some people is a little bit trickier though, because some people forget what that exponent is that always gives us an answer of 1. Anything to the power of what is 1? 0, yeah. And so since anything to the power of 0 is 1, that's what we get here is just 0 as our answer there. All right, so these are the kind of those themes that are winding throughout the year, and each time we kind of add a layer of complexity to it so that by the time we get into the tougher problems, we'll have already done most of the complexity. But of course, we also need to take a look a little bit more at the problems that we've just been doing in this unit and continue practicing those. So this is the last problem that we're doing today, because this does follow up on what we've been doing last week, and, well, it's a big problem as well, as you'll see. But not perhaps as big as maybe you fear, at least. We'll see. All right, so the very first thing we need to do is we need to start by identifying what our variables are going to be. And to figure that part out, I'm always looking to see what question is being asked in this problem. And this one is asking how many people were in each section. So that means that I have the 100 as one variable, the 200 levels, and the 300 levels as my other variables. So notice there's a total of 3 variables then. Now, I'm just going to go ahead and be arbitrary about it. I'm going to call them x, y, and z. Normally, I like to use letters that actually represent something meaningful for what they represent, but since they're just 100, 200, and 300, there wasn't anything that would make that particularly relevant. So, we're going with x, y, and z for each of those, and yes, you want to start by identifying what each one represents. And then I need to start looking to write some equations to deal with this situation. The first thing that jumps out to me, at least when I take a look at this, is I see a lot of numbers that deal with money. And so each of these numbers that deals with money, I can then take each of those and write a single equation that encompasses all of those. So like if it's $20 per 100 level seat, well, the 100 level seats are the x's. What would I do with the 20 and the x's to figure out the amount of money from the 100 level seats? Yeah, we'd multiply them. We'd just get 20x there. All right, and so then if the 200 level seats each cost $10, I gotta be doing the 10 times y. And of course, $5 per 300 level seat means 5z. Now, if I take all of those, I want to be able to get this 110,000 as my total. What would I be doing with the x, y, and z values that I'm talking about there? We just add them up. And when I add all of those with the multiplication, it should then equal that total value. So there's my first equation. All right, now that I have that equation, I need another equation, because of course there's three unknowns, right? So I'm going to need three equations. The next number that jumps out to me as I take a look at this then is the 10,500. Well, that means I can have 10,500 over here as like my total. But what would I do with x, y, and z to get 10,500? Well, really all we got to do is just add them, right? Because if I take the number of 100 level plus the number of 200 level plus the number of 300 level, all those together is going to represent the total number of seats, the 10,500. So far I've got two equations, but I still need a third. Because of course, if there's three unknowns, we have to have three equations. So for this last equation, well, I'm going to have to go up and I'm going to have to make use of this fact that we are told that there are twice as many people that bought tickets for the 300 level as for the 200 level. And statements like this tend to mess with us a little bit, because I know I'm going to be having a z and a y, and I'm going to have to be multiplying something by 2. But we end up going actually round and round whether it's going to be 2z equals y or z equals 2y. And it really seems like it could go either way at first. And so whenever you're faced with one of these, because it seems slightly ambiguous, let's actually test a number and see what happens here. So let's say that I have a z value of 8. Okay, so remember z, that's my 300 level tickets. So if I have 8 of the 300 level tickets, twice as many people bought tickets for the 300 level as the 200 level. So then how many would there be in the 200 level? If there were 8 in the 300, it would have to be 4. And so in order to set them equal to each other, which one am I going to be multiplying by 2? The z or the y? The y. Yep. It has to be z equals 2y, which it throws us off sometimes because we see the word twice and then the very next thing we see in that sentence is 300 level. And so we assume that that means we should be doubling the 300 level, but you see that isn't the way it worked out. So you really have to kind of think this through about which way it gets constructed. All right, so now that I have that, I now have my three equations for my three unknowns. I can solve this. But do you see what your first step would be in solving it? Maybe, maybe not. Because this one we actually can start utilizing some other techniques that we haven't had to use in our standard 3x3s. When we were first learning how to solve 2x2s, remember, we first learned how to solve them by graphing. Don't worry, I'm not going to make you graph this. And then we did substitution method, and then we did elimination method. Well, when we've been solving these 3x3s, basically everything's been elimination. But you actually can use substitution with it too. And that's what we can do here. Because you'll notice we got this z equals 2y. Well, and if z equals 2y, then I can take that z value and I can replace all the other z's with the 2y. So I'm going to be taking this 2y and I'm going to plug it in for z there. And I'm going to take the 2y and I'm going to plug it in for the z there. If we do that, at first it doesn't necessarily look like we made a lot of ground. But this actually is setting us up beautifully. It's going to help us out a lot because, well, I can simplify it. For instance, I can do the 5 times the 2y. Okay, that's easy. That's just 10y. But notice now, I have 10y plus 10y. Those are like terms that I can combine. So I'm going to want to do that. I'm going to combine those like terms. And the same thing happens in the second equation. The y plus the 2y. I can add those like terms. And if I do that, once I've cleaned it up, notice it's a lot easier to see how this helped us. It left me with a 2x2 system of equations. And just like our previous problems that we've been seeing for weeks, I'm trying to take my 3x3 and turn it into a 2x2, because then I can solve it from there. So now that we have it down to our 2x2, go ahead and solve it from there then. And so once we get our 2x2, we need to choose a variable to cancel out. I do like the x's because I see that I can multiply just one of the equations in order to be able to make them eliminate. So I'm going to be eliminating the x's by multiplying the second equation by negative 20. And then we find our y value, which should be 2,500. Once you find your y, well, now you can go and find your x and your z values separately. And so now that I've found my y and I do want to go find those other variables, I need to make a choice about which one I'm going for next. And actually, you could go either way in this particular problem. But my habit has been, in all the other 3x3s I've solved, is once I find a variable by like solving a xy system, I take the y and I plug that back into find x. And so this looks like the easiest equation of those to work with. So I'm going to plug the y into that equation and then figure out what my x would be that goes with it. And so when I do that, I can go ahead and find that x equals 3,000. And then I need to find z. And to find z, I can still take both the x and the y and plug them into the first equation. Or I could take x and y and plug it into the second equation, which looks even easier than that. Or, notice the third one. We actually could have used this before even finding x, and we can still use it now as well. Because z just equals 2y. So if I want to know z, I can just take the y value that I found and multiply it by 2. And so then we find that z equals 5,000. That's all we had to do. You could find the same thing with the other equations as well, but I think that one's a lot easier. And so having worked that through, we then have found out that there would have been 3,000 of the 100 level tickets, 2,500 of the 200 level tickets, and then 5,000 of the 300 level tickets. And we're done. Mostly in this problem, what was new and different was just the fact that we were having to write the equations ourselves from the words. But once we had them written, same basic idea as what we've been doing, right? Solve the 3x3 by turning it into a 2x2, then solve the 2x2.